So last time we talked about law of sines and cosines or law of sines stuff. Did you guys have questions from the homework or anything before we kind of get started into new things? Yeah, Giselle? On number 11? Sure. Oops, that's not what I want to do. Stop. Okay. All right. So if we look at the directions on number 11, it says that two triangles can be formed. So we already know that this is a two triangle situation just from the direction. I'm going to go through and kind of show you why I know it's a two triangle situation just as some additional review. This part is not necessary to do the problem because you're told there's two triangles, but it's worth kind of going over because it can be kind of tricky. So I would start by just drawing the picture. So right away, I notice that this is a side-side angle because the given angle isn't in between the two given sides. I notice that the given angle is acute, and I notice the side opposite the given angle is the shorter of the two sides. So this is that ambiguous case situation. So to figure out how many triangles I have, I start out by setting up a law of sines to solve for the only thing I could, which would be angle B. I don't know why I wrote A there when I wanted to write the number. And I'm going to get sine B by itself and evaluate what I have here. So I'm going to look at what that number is, 17 times sine 64 divided by 16. Based on the size of that number, I'm going to either know that I have one triangle, two triangles, or zero triangles. So if that number was bigger than 1, I know there's 0 triangles. If it's exactly 1, it's 1 triangle. If it's less than 1, which is what we have here, I know it's 2 triangles. But we also knew that just from the direction, right? So let's go ahead and actually solve for the parts on those 2 triangles. So we'll start by finding angle B first. We also need to find angle C and side C. I'm going to put a 1 subscript on each of those to indicate they're the measurements for triangle 1. To do sine B, or to start with angle B, I'm going to start with just this equation and then solve it for angle B. So I'm just going to do the sine inverse to both sides. So when I do that, I'll do second sine, and I'm going to use the ants command, so I'm going to take all the decimal points with me. So I get 7274. And then for angle C1, then I know that since I know 2 of the 3 angles, I can find the third really easy. Were these the same numbers you were getting, Giselle, or was this?
My issue was I just put like 0.95 instead of like the rounded instead of just doing it.
Yeah.
So that was
Yeah, that's that would have been my guess. That it would have just been like a little bit of a rounding issue. In general, I like using the ants command and taking all my decimal points with me. Now, if on the test or whatever, I'm probably going to just ask you to round to the 10th.
Okay.
So like, if you just take 2 or 3 decimal places with your answer into your calculator, it probably will be fine.
Okay.
But like, that's where it's happening. It's just from the rounding. I'm going to finish this one out for anybody else that was still interested in seeing the end of this thing. Again, good review. So there's my answer for angle C. And now that I have angle C, I can write another law of sines to solve for side C. So I'll do sine B over B. And again, I suppose here I could use sine of C over C, but I don't want to use rounded stuff if I don't have to. Or I meant sine, I use B over B. But I don't want to use the rounded stuff if I don't have to. And then last time on the calculator for this set of answers, and then we'll go to the other set. And again, I'm going to use that ants command, so I take all the decimal points with me of that previous one. Again, not super necessary that you do that, but you'll get a little bit more accurate answer. So that's about 12.20. So those are my 3 answers there. For triangle 2, I'm looking for the same 3 things. To get angle B2, though, the nice part is that that's just going to be the supplement of angle B1. So the first angle I solved from triangle 1, I can find the corresponding angle in triangle 2 by just finding the supplement to it, which is lovely, right? No law of sines necessary there. I just need to do a little subtraction. So I get 107.26 there. And then to find angle C2, I can do the same thing. Angle B is still 64. That part's constant in both triangles. But I'll use my new angle B. I meant angle A is still 64, excuse me. But I'll use my new angle B. So that's 8.74. And then I set up the same law of sines problem, but in this case, I'm using my new angle C. So 271-ish. Obviously, you were fine before that. Is that okay with everybody else on kind of what we did there, running through, seeing that again? Again, this is the most complicated thing, is where you have to identify that it's this weird case, and then sort through both sets of answers is probably the most complicated thing we do in this section, or this chapter, I should say. So seeing another example, one that you might have actually worked on also is nice. probably for everybody involved. Eventually you'll have worked on it. I don't know, maybe some of us haven't started the homework yet, and that's okay. Ideally, you do some of it even before the next class. The learning goes better if you are doing that rather than waiting till last minute. Others, Elena, did I see your hand up earlier? Same question. Okay. Did I see anybody else that had questions on stuffs? Okay, very good. So today we're going to be doing sections 7.3 and 7.4. So 7.3 is about the law of cosines. We're not going to prove the law of cosines here. I'm just going to kind of drop this in. So again, for a non-right triangle, ABC, with side lengths named based on their opposite vertex, we can say the following. We say that a squared is equal to b squared plus c squared minus 2bc cosine a. What does that formula remind you of? Looks like the Pythagorean theorem, and we've just added on some additional correction factor because this is not a right triangle. That's essentially all that's going on here. If this was a right triangle, if A was a right angle, remember what cosine of 90 degrees is? It's 0. So what happens if you're working in a right triangle with the law of cosines? The last part just drops off and you have exactly the Pythagorean theorem, right? So again, should remind you of the Pythagorean theorem because it is actually just a generalization of the Pythagorean theorem. So if you try to do the law of cosines on a right triangle, the last term there would just kind of drop off to 0, and you'd be left with just the Pythagorean theorem. So when do we use the law of cosines? So remember last time, for angle, side, angle, 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 side, and side, side, angle, we used the law of sines. For our other two situations, we're going to be using the law of cosines. And I'm going to put a little asterisk by the side, side, side situation because there's some additional checking we have to do in a side, side, side situation. And we'll talk about that in a moment. Let's do a couple of examples now. So we're asked here to solve the triangle ABC that has the following measurements. So I'll just kind of start my usual way and draw myself a picture. If I look at that picture, which situation am I in? Side angle side or side side angle?
Side.
Side angle side, I can tell because the angle's in between the two given sides. So that tells me I should be using law of cosines. So what quantity will I be solving for first with the law of cosines? Not an angle. Side A. Yeah. So I'll say a squared is equal to b squared plus c squared minus 2bc cosine of angle A. in a side angle side situation, it's easy to tell which you're going to solve for first because it's going to be the side length that corresponds to the given angle. We're given angle A, we know we're going to be solving for side A first. Everybody's okay with that? All right. This is the equation for A squared. I want just A. So what do I have to do to get just A? Square root both sides. When we square root both sides of an equation, what happens? What do we get? Plus or minus. Now, A, it represents the length, a side length in a triangle. So do we really want the plus or minus? No, it's always just going to be the plus. So I'm not going to bother even writing that stuff. I'm just going to talk about it because we're being thorough. But at no point when I'm doing a law of cosines and solving for a side length am I ever even going to write the plus or minus. I'm just going to always know that it's positive because we're talking about the side length of a triangle. And I'm not going to bother doing any kind of simplifying beforehand. I'm just going to type this into my calculator in one line. Oftentimes, if students make like order of operations mistakes, it's because they're trying to do this in like multiple stages rather than just like in one line in their calculator. If you're just doing it in one line in your calculator, there's very little chance that you're going to make a mistake. If I type that in, I get 951-ish. Okay. All right. So now we have to solve for either angle B or angle C. Do you suppose it matters which one we do first?
Yeah.
It definitely matters in this case. Why all of a sudden is it mattering when it didn't matter before? Because it's going to be an SSA situation. If I'm solving for one of these other angles, I now have an SSA situation. So I want to do everything in my power to avoid running into that ambiguous case. Everybody's okay with that? That's why all of a sudden the order in which I do this is going to matter, because I don't want to run into the ambiguous case and have to grind through two sets of answers and try to figure out which set of answers is even the correct set. So the way we do this is we just find the smaller angle next. So between angles B and C, which one is going to be the smaller one? Angle B, very good. How can you tell? Because side B is shorter than side C. Everybody's okay with that? Now if I use this little hack, I am guaranteed with my law of sines to not run into the ambiguous case, so I can just treat this as a one triangle situation. I don't have to think about it any further. Everybody happy with that? I would be, right? Like, let's keep it simple. So I cross multiply, divide, and then do sine inverse. I'm just going to do that all in one step. Does anybody object to me doing that, considering we've just done a bunch of problems or a bunch of examples where we solve the law of sines, right? It's not like we haven't done the algebra there. For the sake of just saving some space and like reducing the amount of writing, I'm just gonna not deal with all that extra showing all that extra algebra. So I get 55/44. And now that I have two of the three angles, I can solve for the third one. What's that got to be, like 90.56. Okay. So the one thing you need to remember with that side angle side is after you found that third side, find the smaller angle first. Again, compared to the SSA's case, that's not so bad. Let's do a side situation next, huh? Now this one should be able to look at this and immediately recognize that this is side. I don't even have to draw the picture. How can I tell? I don't have any angles. They're all side lengths. Yeah, I can tell just from the problem. Without even having to draw a picture, I can tell the case. That's the easiest one to identify. Now, question for you. If I just name 3 numbers and I want to use them as side lengths in a triangle, can I create a triangle out of any 3 side lengths?
No.
Like if I give you 1, 1, and 10,000, can you make a triangle with those side lengths? No. Definitely not. So not every 3 side lengths is going to correspond to a triangle. We must check that before we start. In any SSS situation, got to check to make sure it's possible to form a triangle with those 3 side lengths. Does anybody remember the rule from geometry that's going to tell us whether the 3 side lengths can form a triangle or not? You do some adding, that's true. It's okay that you don't remember because you almost never use this in geometry. The rule is just that leg plus leg must be greater than the hypotenuse. And if that's true, you got yourself a triangle. If it's not true, there's no triangle possible and you're done. Okay. Everybody's good with that? So we're going to solve for an angle now. We have enough information to solve for P, Q, or R. Do you suppose it matters which one we solve for first? Yeah, it's going to make a difference. Okay, which one do we want to have? And again, the reason that it's going to matter is because it's going to generate an SSA situation later, right? So which angle do we want to find first? Not the smallest. We want the biggest. The reason we want the biggest is because hopefully the biggest angle is going to be obtuse, which will create an SSA situation where there's guaranteed to only be one triangle. I can't get an ambiguous case next. But do all triangles have an obtuse angle in them? They do not. So finding the second angle also might matter. What is the largest angle in this problem? Angle R. So we'd write that like R squared is equal to P squared plus Q squared minus 2PQ cosine R. And I'm not going to fill the values in here right away because what I'm going to do is I'm going to solve this symbolically for angle R and then use this to kind of generalize the law of cosines where I've already solved for the angle. So it's just going to create a new formula that will write alongside the old ones. So we don't have to do this algebra every single time. Is everybody okay with that? All right, so my goal is to get R, the capital R by itself. And I'm solving this. What's the first thing I would want to do to get the capital R by itself? Just normal solving algorithm. Good. Subtract p squared and q squared from both sides. Again, when we're solving, we're just running the reverse order of operations. The first thing we want to undo is addition and subtractions to the variable anyways. Everybody's okay with that? Next thing we want to do is divide by negative 2pq. Absolutely. And then the last thing we would need to do is cosine inverse to both sides just to get the R by itself. So in doing this, I'm going to go back to my law of cosines formulas and just update these to give a second formula where I've got the angle now isolated. Oh my goodness, Mr. Kulik. What did I forget? Yeah, come on, dum-dum. It's the beauty of doing it in OneNote rather than in pencil, huh? Then just scoot it over a little bit and slide that in there. So I'm just using what we just created together to just update these formulas so that I have the angle by itself, just so I don't have to do the algebra over and over and over again. Not that the algebra was difficult or really that time consuming or beyond the scope, but like we do this a lot. It's worth just having a formula for it, even if it's just a simple rearrangement of the law of cosines. Fine. Does everybody feel okay with what I did there? All right. Let's go finish this example up that we had kind of put on hold here. All right. So we say that R then is the cosine inverse of 10 squared minus 5 squared minus 8 squared over negative 2 times 5 times 8. As an FYI, here's a case where you definitely want to use that fraction command to enter this in because the parentheses are super annoying. So I'm going to do alpha y equals, pick the first option. That gives me like the fraction bar. So I can type this in exactly like it looks on my sheet of paper. And in one of these law of cosines problems, if you start getting answers that just make no sense, it's likely you've just run into a zero triangles problem and you didn't recognize it. Like if you do cosine inverse and get like a negative angle or something. Well, you can't get a negative angle. But if you get like, you do cosine inverse of this and you find that like angle R is now smaller than the angle at the end or something, you're like, well, that's not right. The problem probably was that you didn't recognize that there was zero triangles possible. It was you're in an impossible situation. Next. Now notice this is an obtuse angle. So if I do an SSA with this, I'm guaranteed to just get one triangle, which is fine. Now, if this was acute, I have to be quite careful again. When I'm using the law of sines, I want to find the smallest angle first. And I'm just going to always do that regardless of whether my angle is obtuse or not, because I don't want to get in the habit of not just doing this so that I make a mistake later on when I get going fast and I'm not thinking about it. So in this SSA case, biggest angle with the law of cosines, smallest angle with the law of sines. And I'm just always going to do that whether I need to do it or not. In this case, I didn't really need to do it, but I'm just going to do it in that order because I'm going to forget when it runs into a case where I have to do it. It's just one less thing to think about if I just always use that same order every single time. So we'll say sine of 97.90 over 10 equals sine of p over 5. Again, I know p is the smallest angle because p was the smallest side. So cross multiply, divide, and take the sine inverse. And again, notice I'm doing that ANDS command whenever possible so I can take all my decimal points with me. I'll get a slightly more accurate answer. So that's 2969. And now to get my last angle Q, I know 2 of the 3. So I'm just going to do the triangle sum theorem. So I'm going to subtract those 2 from 180, and I got my answer. So 5241. Feel okay doing this? Again, not bad, right? Law of cosines usually easier to use than law of sines. The only tricky part is remembering to do the checks, right? So you got to check to make sure the triangle's possible, and then you have to solve things in the correct order. With the law of sines, the order in which you do things doesn't really matter. Law of cosines, you do have to be careful about the order you're solving for the remaining pieces. But the algebra is pretty easy for all this stuff, right? Nothing super complicated. All right. 7.4 is just about the areas of triangles. So if we go back to geometry, what's the area for a triangle? The formula for the area of a triangle? 1/2 base times height. Great. So if I have some triangle that I've drawn here, what part's the base? Yeah, one of the side lengths you can call the base. The bottom's fine. So what's the height then? Yeah, it's the altitude. It's the perpendicular line to the base that intersects the opposite vertex. What's the problem here with the height? It's not a side length, right? If you're not given that height, is that going to be easy to find? It's kind of a hassle. So what we're going to do, our first order of business is going to be to come up with some area formulas for triangles that don't involve the height, that only involve side lengths and angle measures, since we've just spending all this time solving for these things. Everybody's cool with the plan? Okay. So I'm going to go ahead and just label this triangle. So I'll call it ABC, so that the B for the base that we wrote in is the same as the side name of that side. So what I notice here is that this is a right triangle. So I can say something like sine of A is equal to opposite over hypotenuse. That gives me a formula. I can solve that formula for H by multiplying both sides by C. And if I then take my original area formula for a triangle from geometry and substitute that new value for H in, I have an area formula that does not involve H at all, just side lengths and angle measures from my triangle, which is rather lovely, right? We can, depending on what stuff you're given, you can then use or kind of write this in three different ways. So depending on whether you're given angle A, angle B, or angle C. And if we look at what we had just done with triangle ABC here, we need a side C, side B, and angle A. We notice that this is particularly useful when we have a side angle side situation, right? What would we do if instead you're given like an angle side, or a angle side angle, or even an SSA situation, and we wanted to find the area of a triangle like that? I'm just going to use the law of sines till I get a side angle side, and then I'm just going to use my formula. So I might have one additional step in there where I have to do a law of sines to make a side angle side piece in there before I can use the formula. What case haven't we talked about yet? Side, side, side. We're going to create our own special formula for that. And I'm going to do the derivation of how we come up with this formula. So what I'm about to do is something that you wouldn't have to repeat. I'm just doing this to show you how we arrive at the formula I'm about to give you. Okay? And this is for a side, side, side situation. All right. So we know that we have like area equals 1/2 AB sine C, right? Okay. So what I'm going to do first is I'm going to multiply both sides of my equation by 4. And then I'm going to square both sides. And I remember that sine squared is the same thing as 1 minus cosine squared. And now I'm going to just distribute that 4a squared b squared through. And if I look at that last term, I can think about that as 2ab cosine c quantity squared. Did you guys recognize that from somewhere? That's part of a law of cosines, right? So all I'm going to do is rearrange to get that piece by itself. So I'm going to add that piece over and then subtract the c squared. And now I'm going to make a substitution back into my main equation here. And actually, I'm going to write that first term as something squared. So if you look at the right-hand side of my equation, that should look like a difference of two squares. Something squared minus something squared. Do you guys see that? What do you suppose I'm going to do with that? I'm going to factor it like a difference of two squares. Is everybody okay? All right, I'm going to do some clever rearranging here. So I'm going to go ahead and distribute through my negative sign. So I'm going to write c squared first. I'm going to have minus a squared plus 2ab minus b squared. And over here I'm going to have write it as a squared first plus 2ab plus b squared, and then minus c squared last. So in this first quantity, I'm going to factor out a negative sign. And the second quantity, I'm just going to leave exactly how it is. And then I notice, aha! I recognize this. Those are both perfect square factoring patterns. So I'm going to factor those parts. Aren't you glad that you'll never have to repeat this process? Look at what I have now again. I have two differences of two squares. Guess what I'm going to do? Factor those. Oh my goodness. Oops. So if I rearrange this, I'm going to have C plus B minus A. And then I'm going to have A plus C minus B. And then I'm going to have A plus B minus C. And I'm going to have okay, A plus B plus C. Now I'm going to define a new variable. I'm going to define S as A plus B plus C over 2. We call this the semi-perimeter. Semi because it's half, and perimeter because A plus B plus C is the perimeter of a triangle. So if I look here, let's see, this is going to be 2S, right? So I'm just going to write that part first. This piece is going to be (2s) minus 2a. If you make some common denominators, and you'll see that that is what that works out to be. The next piece becomes 2s, oops, is it 2a, minus 2b, and then that third piece becomes 2s minus 2c. Notice each of those quantities has a factor of 2 in common. So I can factor that out. And since this is all multiplication, those 2's can just all multiply together. We'll divide both sides by 16. And then to get just area, we square root both sides. To get this, where S is that semi-perimeter. Woo! Again, when I did the square rooting, it creates a plus or minus, but since we're talking about an area, obviously it can't be negative. Now, would I ever ask you to generate this again on your own? No. But part of an honors class is we're going to prove things. Now, something like this is just like a big mess of alphabet soup of confusion at points. But nothing in here I did was like things that you weren't comfortable doing. It would be, can I link all this stuff together on my own to do this? Probably not, but that's okay. Conceivably, it would be within your abilities. This formula actually has a name. It's called Heron's formula. I believe Heron was an Egyptian mathematician, but I think he was probably really Greek, because it would have been, I think it was post-Alexander the Great, where all the Egyptians were really Greeks. Because I think he was in Alexandria when he did this. Maybe. All right, so let's do a couple of examples, and then we're going to get out of here. Sound good to you guys? All right. So it says find the area of the triangle. I'm going to start by drawing a picture because I'm not sure if this is a side angle side or side angle, and well, the picture helps me. I can tell right away now from my picture that this is side angle side. So I can just use my side angle side formula. So 1/2 B times C times sine of A. Nothing more to it than that. Just going to plug into my calculator now. So I get 9207. Now the units on the B and C were millimeters. What should the unit here on our area be? Millimeters squared. Is Mr. Kulik going to be picky about that on the test?
Yes.
Yep. Okay. If the problem has a unit on it, you better be giving me a unit in your answer. And you're like, really? That seems like unnecessarily picky. Well, I'm telling you though, I'm not just like letting you find out later. I'm telling you that like, hey, I'm gonna be picky about this. So like, that's something, right? All right. This situation, what kind of situation are we in? Side, side, side. Before we apply Heron's formula, what do we need to check first? Is this triangle possible? Yeah. So 5 plus 8 is greater than 10. Yes, sir. I'm good. So I'll start just by calculating my semi-perimeter. So it's at 23 over 2. I'm going to call that 11.5 since it's a terminating decimal. So my area is going to be the square root of S. And then S minus A. What's 11.5 minus 5? 6.5. And then S minus B. What's 11.5 minus 8? 3.5. And then S minus C. What's 11.5 minus 10? Well, 1.5. And then I'm just going to go to my calculator and type that in. The arithmetic's really easy, and it saves me like a whole truckload of button pushings just to do some subtraction on my hand or by hand. And unless the side lengths were like kooky decimals, it's pretty easy to do. So I get 1981. What should the unit on that be? Meters squared. Yep, if you don't have the squared, it's not right. But that does it. And what did we do today? We closed chapter 7. So for the homework on for Sunday, you can add to it 15 through 30. What do we do once per chapter that we haven't done yet? Homework quiz. What would I expect next time? Homework quiz. What should I be able to do? Law of sines and cosines. Should be able to do those to solve triangles.
So it could be like this stuff that we learned today too.
Could be some law of cosine stuff. But I think that's better than just all law of sine stuff, right?
Yeah.
Because the law of cosine stuff is pretty easy in comparison. So tentatively, then Wednesday will be a review day. We'll do the homework quiz and the review. And then Friday be the test for chapter 7. Oh, yeah. So we don't have school on Monday. So yes, then Tuesday, it's Martin Luther King Day. So just FYI, that's a coming.